So start us off by reading number 1, Sam, for us. All right, and number 2, Danielle. Okay, so here's what we call a bar graph. You probably have seen these before, either in a class or just picking up a newspaper or a magazine. Notice every graph that you produce, whether it's for a project or later on when we're doing other things, you always want to make sure there's a title. So when you look at this title, you know what the variables are and the information that you need to interpret the information given in the graph. Notice that each axis, the vertical axis has a label and the horizontal axis has a label. The only thing that is missing from here, as far as I'm concerned, is on tuition and fees. You always like to see the unit, so I would put something like this, dollars, after it. Okay, so just give me a sense of what maybe your group came up with or what you came up with in terms of looking at this bar graph and an observation that you may have made about it. Any observation whatsoever. Yeah, Paul? Okay, from 2000 to 2010, tuition and fees, the average tuition and fees at public colleges, did you say steadily increased? Steadily increased. Okay, that's good. All right, that's one way to say it. And I like the fact that you actually use the time period, which is important to know. Other observations, even if it's similar or just maybe another way of saying some of the same things. Nobody has anything else that's different than that? Yeah, Danielle? All right, the average cost of tuition and fees nearly doubled in the decade from 2000 to 2010. No, I don't think I've ever had anybody notice that before. That's good. Thank you. Others? Yeah. Okay. Yeah. And Claudia says that the largest growth is between 2003 and 2004. Students tend to notice that. My first class missed that. That was like not missed it, but nobody at least voiced it. But usually someone will always say the largest jump was from 2003 to 2004. The largest growth or change in the average cost was in those years. Okay, anything else? Anybody say some of that in another way? Anything else you want to? Does anybody use the word linear? Yeah, what you have for that? It's a positive linear bar graph. Okay, let's tear that apart a little bit. Positive linear bar graph. Okay. So what do you mean by can you remind me your name again? Sorry. Paige. Paige, can you remind me what you mean by positive? That's correct. But there's something going on when you say positive. So I'm just trying to kind of grab that a little bit. Right. So you're noticing as the year increases each year, that your tuition and fee is also increasing. Yeah. We call that a positive correlation. Someone in my first class used the word correlation. We'll be talking about that a little bit later on when we look at linear regression. That's a statistic that helps us to measure how strong that linear regression is. It's called a correlation coefficient. But we don't need to know that right now. And linear, is this relationship linear? No. How many say no? How many say yes? And how many say I have no idea? How many say no? So I got 2 here, 3, 4, 5, 6. 6 people say no, it's not linear. How many people say yes, it is linear? Well, can I put you in, Paige? All right, she said it was linear. How many people say I don't know? Oh, the rest of you. All right, rest. Okay. So Paige said a positive linear bar graph. Then 6 of you said it's not linear. So why is there a discrepancy here? Someone who said it's not linear. Why is this not linear in your mind? Ira?
Because it's not growing at a steady rate.
A steady rate. What is another word for steady rate? That you constant rate. Yes. So in other words, for this to be a linear relationship, an exact linear relationship, if you took the number of years, let's say after 2000, this is a typical thing that we do when we're working with data sets like this that has the actual year here. Notice they're saying ending year in the school year. So the ending year in 2000 is 0, because that's how many years after 2000 it is. The year 2001, the ending year is 1 because it's 1 year away from 2000. And this would be a 2, and this would be a 3, this would be a 4, all the way up to 10. I usually like to define it as the number of years after 2000. 2000 I'm using as my base year. I could have picked 2005 if I wanted to. And if I did, then 2000 would have been a negative 5 because it would have been 5 years before 2005. Just depends on what you pick as your sort of starting point. Okay, so I'm picking 2000. And then the vertical axis is measuring the average cost of tuition and fees. So let me clear this up a little teeny bit here. So if we were going to record our actual values in the year 2000, which were given the number 0, the tuition and fees were $3,362. And let's pick a year like 5. The year 2005 was 5,132. And again, how I got each of these is I took 2005 and I subtracted 2000 from it. This is our base year. That gives me the number 5. And here we have 2000, take away 2000. So for the year 2010, we'd have 2010, take away 2000, gives me 10. And that's $7,020. So for this to be linear, I can pick any 2 points on that graph. So this first point could be, we could use the ordered pair 0, 3, 3, 6, 2. And for this second point here, 5, then 5,132. So if this was linear, then the change in our independent variable or our horizontal variable, or in this case, our number of years, the rate of change between that, so let's say 5 take away 0, and the change between the tuition, 5,132 minus 3,362, that rate of change, that rate, which is a ratio, has to be the same if I picked the next 2 points here, 10 and 7,020. If that rate was constant or steady, as you mentioned earlier, then this would be a linear line or relationship. So if we look at this, we have a 5 in the denominator, and I have to call upon my calculator here to do this subtraction and then the division. 5132 take away 3362 gives me 1770. And when I divide that by 5, I get $354 per year. So that's dollars per year. So from 2000 to 2005, the average cost increased $354 per year. So all you would need to do without even doing the rest of this calculation is if from year 2000 to 2001 it didn't increase by $354, which it clearly didn't, then you know this is not a constant rate of change. So for this to be linear from each year, from 2000 all the way up to 2005, they would have to increase by 354 each and every year. And if you actually did this particular one, you would see that it's actually a little higher than 354. Okay, so it's not linear. However, the fact that Paige noticed that there is a linear trend going on will help us when we try to find what we call a model for this data. And it's also the model that we used in this project. You will have a linear model for this your first project. Let's see what else is going on. Oh yeah, the little, whenever you start a graph on one of your axes or both, you do not start at 0. You have to put this little break in the axis, which is just like this little, like, I don't know, it's like a squiggly. I don't know how else to explain it. And what this does is it actually exaggerates the differences. And you'll see when I plot these points starting at 0, how it looks a lot a lot straighter than it does now. All right. So you are all students in public higher education, and we now have information in front of us for the years 2000 and 2010. This is 2016. What might you want to know? What question might you be interested in asking, and hopefully having a model help you find the answer? Ian?
What's the tuition by the end of 2017?
Oh, what's the tuition average cost? Notice how I'm taking what you're saying and I'm being a little more explicit. So on your projects, when you're answering your projects with sentences, you want to use your variables. So your variable here is the average cost of tuition and fees at four-year public colleges, right? So you want to actually use all of that language in your answers, in your full sentences. So what's the average cost of tuition and fees at four-year public four-year colleges, U.S. colleges in 2017? Right? That's a question you might ask. Anybody have a young child? Okay, Danielle, what might you be interested in? How old's your child? You have 3. What's the youngest? 7. So what might you be interested in? Yeah, what's going to be the average cost of tuition and fees in 10 years? So ditto, ditto, ditto in 10 or 15 years, okay? And believe it or not, I actually found something last night, 2 bar graphs that showed the average cost right now, and that included room and board at private schools, public four-year schools, and community colleges. They did it now, and then they actually had a bar graph that showed 18 years from now. It was really interesting. So it's like if you had a child born today. And looking at it, and they're assuming the same rates of growth. Right now, it's about 5.9% each year in private schools. That's a different type of function than linear. That's what we're going to look at the end of the year. It's called exponential. If it continues to grow at 5.9%, you wouldn't believe the costs. It was scary. I don't think let me see, let me look in my Dropbox real quick to see if I put it in there. I put a couple things in my Dropbox when I was doing this last night. Let me just shut that off for a minute. So according to the College Board, the average cost of tuition and fees for the year 2015 and 16. So our bar graph goes up to 2010. So we can see how good our model is going to be by looking at these figures. School year this was what it was at a private college, 32,405, and 9,410 for state residents at public colleges. Okay, so this is going to be the cost, the average cost of tuition and fees. This is real data. It's not using a model and predicting. So let's keep that in mind, 9,410, and we'll see how we do when we actually use our model in a few minutes. And I did put something else in here. India car projections. I found this. I thought this was interesting. Look at this. This is a model, which we're going to be talking about in a few minutes, because right now it's 2016, and they're using some type of model to project the number of private cars in India for the next 4 years. And as you can see, that is definitely a linear relationship. Maybe it's some other type of relationship. Without the actual data, we can't find the best model. But just looking at the trend, you can see there was this particular person who's trying to make a lot of money. India has quite a few people, right? And they're trying to increase the number of private vehicles owned there. So not very good for the environment, but we'll see. And then I did find something else. Here we go. This is public schools. Where's GeoGebra? How do I get there? It should be in here. Look for appropriate program. Okay, here we go. I'll do that while you're working. I did actually find Massachusetts data. So as you can see, you would, as students, you have a lot of questions about average cost of tuition and fees. Some of you will maybe going on to the university. Some of you may be going to a private 4-year school. Some of you may be going out into the workforce for a while. But often in mathematics, we try to pin down the relationship between two variables so that we can use that relationship to answer questions. Okay, we all have questions, all right? Whether that's about climate change or pollution, or in this case, the average cost of tuition and fees. So someone want to read number 1 to us, please? Yep, go ahead, Ian.
So we go. Good news is that it may be possible to answer your question using mathematics. We can work with the real data collected and presented in the bar graph to find a mathematical model.
Let me turn the, so here's our points graphed. And if I asked you what type of graph might explain that relationship or come as close as possible to all those points, what might you say? What type of graph? A line, right? So let's try fitting a line. Guess what? I had GeoGebra do it. And there's the line that fits as close as possible to each of those real data points. Okay. The equation for that line is right here. I'm just going to open this up right there. You'll probably see that in your project. That's a slope. There's your value for x, and that's your y-intercept. So that's the model of that line right there. All right. What about a parabola? What do you think about a parabola fitting that? No? You don't think a parabola would fit too well? All right, let's take a look at it. I'm going to fit a parabola to it. Oh, look at that, the green line. Not too bad. In fact, that green line is actually, it's not cheating. Someone say it was cheating? The green line is actually a little closer to all those points than the straight line, isn't it? So let me show you what this looks like, how it's a parabola. I'm just going to notice how I'm doing this. I'm grabbing this 4-way arrow and I'm moving my axes, see? And I'm moving that all about. And there's your parabola right there. So the parabola, remember, is right there, and it's extending through that data set. And it is actually closer than the line. And you can see that by spreading out the scales here. And you can see how the green part of my parabola actually is closer to all those points than the line. Both of those models are, both of them, they're pretty darn good, aren't they? They're really close. It just happens that the parabola is a little better at predicting and estimating the actual cost and tuition based on this data set. So notice when we go back to our packet here, the formula or the model or the equation, all of these things, it's an equation, it's a formula, and it's a model that we're going to use to describe that trend that we're looking at, that bar graph, is indeed a quadratic equation, which is the type of equation you have for parabolas. Okay, so this model is reflected with this green line. You'll be using the linear line because it's easier to work with linear relationships for your project. All right, so it models the average cost of tuition. That's this variable right here. T is the average cost of tuition and fees. That's our dependent variable. That's what we're solving for. Remember, your dependent variable goes on your vertical axis. The value of t depends on what year we're looking at, and x is the year after 2000, the number of years from 2000, or as they said, ending years after 2000. So let's answer the first type of statement here. Use the formula or use the model to find the average cost of tuition and fees at public U.S. colleges for the college year ending in 2010. So how would I go about using this formula, this equation, or this model, other than Ian, to answer this question? Okay, you plug 10 into the x's. Plug 10 in for x. And where did you get the 10, Eric? Right. You take the year you're interested in and you subtract from that 2000, which is your starting year, and you get 10. So where I see x, I'm going to put in a 10. And then I just have to do a little teeny bit of arithmetic to get my answer. So I get 4 times 100, because 10 squared is 100, plus 3,410, plus 3,194. And has anybody added those numbers together yet? Yep, Paige, sorry. 7,004. Okay. Yeah, and so the dollars will be when we talk about the answer here. So when you're asked a question and you're using a model, it's very important. And you'll see on the back of your graph, I have a little grading rubric. You see this little grading rubric? You do a little self-assessment. If you read each one of these and you can put a check, then you're going to get a darn good score on this first project. I'm basically giving you all the things, all the pieces of this project that I'm going to grade, and all of the points I'm assigning to it. So you just go through there and you do a little self-assessment, and you know whether you've done everything you need to do for the project. Okay. So when you use a model or an equation and you're asking a question, or you're being asked to find something, it's really critical that your answer, your full sentence, describes it as an estimate or a prediction, because it's not the actual data itself. We actually know that in the year 2010, that the average cost of tuition and fees was $7,020. So when you write this sentence, and this is really important for your project, you want to make sure that however you write it, you use the word estimate or predict. If you're going beyond 2010, you would say predict. If you're in the years 2000 and 2010, you'd say estimate. All right. So anybody want to take a shot at writing what sentence you might write to do part A here, 3A, if you were writing this up on your own? And then we can edit it if we need to. Claudia, right? Yeah. Okay, hang on. The estimated cost of tuition and fees at, and I'm just going to do this, public U.S. colleges. Yeah. For the year 2010. Yep. Okay. Good. Estimated cost. According to the model, you can always start off with that. According to the model, right? We estimate, that's another way you could start off. There's lots, for every different person in here, there's a different sentence we could write. The key here is we're estimating. The thing we do in statistics, if you've had a stat course, is you just use this little caret above your variable t, and that helps you to remember that it's not the actual value of t, it's the estimated value of t. So I often do that on my own just to remind me that I'm finding an estimated value. So by how much does the model or the equation or the formula underestimate or overestimate the actual cost that's given in the bar graph? Someone want to help me with that one? Is it an underestimate or an overestimate? But it's under, because 7,004 is less than 7,020. This is the real data. This is the estimate. And we underestimate it by how much money? $16, right? So it's an underestimate by $16, correct. All right, so let's use this formula to predict the average cost of tuition and fees for the college year ending in 2014. I should change that because I have let's do it to 2016 because we actually have that number right here. Did anybody hold on to it? What was it, 9,014 when I showed you? Did anybody copy that down for me? No, but it was 9,014. So let's find the average cost for 2016. This is a prediction based on our model because our model only goes up to 2010. And then we're going to go back to 1990. So I want tables 4 and 5 to do this answer, tables 4 and 5, plus Matt and Kelsey to do this one. And I want tables 1 and 2 and Sam to do this one. Tables 1 and 2 and Sam. And I want you to confer, and once you agree, put up your flags. Look, so what did we come up with on tables 1 and 2 and Sam for the college year ending 2016? What do we get? All right, $9,674. And let's take a look at what the College Board said it was. We can now, it's no longer a prediction because we have the actual data for public colleges. It was 9,410. So now our model is starting to overestimate, right? Remember, a parabola is going to curve up and start to get much steeper. So now notice that our prediction, according to the model, is an overestimate. Okay, still pretty close though. It's pretty darn close. Okay, and what did we have for 1990? Tables 4 and 5. Yep, Cornelia. $184. So does the prediction for the year ending in 1990 seem plausible or realistic or reasonable? No. Okay, and this is something you always have to be aware of. We have a data set that goes from 2000 to 2010. When you go beyond that data set, that's called extrapolation. What we just did here is called extrapolation. That's the real kind of mathematical term for what we just did. When you go beyond the data set, you've got to be really careful because sometimes your model no longer works. Because if you go too far out into the future or the past, the model doesn't capture what was going on then. We call that model breakdown, okay? This is the term that you may want to use somewhere if it happens in your project, is that you're having a model breakdown. Hopefully the project won't cause any of you to have a breakdown. Okay, so it's a model breakdown. And if you think about gas prices, if we were looking at gas prices, say, for the years 2008 to 12, and we created a model, it would show this linear trend. But then what happened in the last couple of years is that that model would not fit the fact that gas prices have plummeted. Okay, so you always have to be careful when you're using these models and you're going outside the data set. When you stay inside the data set, like 2005, 2007, that's called interpolation, IN, instead of extra. All right, let's hit the sets here. I think most of you are pretty familiar with sets. I'm just going to cover a couple of things. Some of it might be new in terms of notation. Ben, you want to read number 5 for us, please? We want to start. So the curly braces, it almost looks like, you can see this on your keyboard. I used to always think of it like a little profile, a person's profile, like you put the eye and the nose and the mouth there, right? Those curly braces say to you the set. So anytime I ask you to write a set in here and you don't use those braces, then you haven't told me that you're writing a set. So this is critical, that you have to remember whenever you write down a set to start it with those curly braces and end with the curly braces. Anytime you have a finite set, like the students in this classroom right now, I could write down each of your names, separate it with a comma. That would be called the roster method. It's not rooster, it's roster, okay? In fact, we call these things the class roster. So your names are the elements. Each of your names would be the elements of that set, okay? So what I'd like you to do right now at your seats as fast as possible, and you can talk to each other if you don't know, you're too young, or you don't have parents that follow the Beatles, is I'd like you to represent the set B, capital B, and that set represents these 4 Beatles that arrived at JFK in 1964. Okay, so see if you can come up with the names of the 4 Beatles that arrived at JFK in 1964. Okay, so what did you come up with? I want to write exactly what you wrote after this equal sign. So someone want to tell me what they have after the equal sign? Exactly as you see it on your paper. Ian?
John Lennon, Paul McCartney, George Harrison, Ringo Starr.
So I'm going to write it exactly like you told me. Yeah. Oh, well, thank goodness. Don't forget my curly braces here to indicate set. If you don't have that down, put it down and make a note to yourself so you don't forget in the future. Something else is missing. Commas. Okay, yeah. I used to have the name of the 7 dwarfs, and that used to elicit a lot of laughter. Unfortunately, for people that were not raised in this country, they often sat there and felt really left out because they weren't read the story of Dopey and Doctor and Snoopy and Sleepy and Sneezy and all that.
Snoopy? I thought he had.
I'm just teasing. Okay. All right, so we're going to use 3 different techniques to indicate sets that are infinite. We can't write every single number that's on the real number line because it's an infinite number of numbers. So we have to have some way to represent sets that are infinite. And since we're going to be talking about number sets a lot in this class, we're going to use something called set builder notation, a graphical representation with the real number line, and finally, interval notation, which you're going to use all the time with your homework. MyMathLab uses interval notation, so you'll have lots of practice with this. The set builder notation is it's a descriptive way to write a set. It's a little more involved than the other 2 methods, and it can be a little intimidating at first, but it basically will start with your curly braces like this, and some expression. In this case, we're often saying the set of all numbers, real numbers. We're assuming real numbers, and we usually use a variable like x. And then we say such that, and how we say such that is with this vertical line. You actually read that as such that. So this says the set of all real numbers such that, and then you place some kind of condition on it. It could be a set of words, it could be an inequality, it could be some statement that you can determine if it's true or false. Is the real number you're looking at meet that condition? If it does, then it belongs in that set. And if it doesn't belong in that set. So the example we're going to use throughout here is x greater than or equal to greater than 2, x greater than 2. So I would read this set builder notation as follows. This represents the set of all real numbers x such that x is greater than 2. That's how I would read that. On a real number line, I would indicate that as follows. And I have a little, I put these little cases at most of your seats. If you want to use a highlighter or a color, I have highlighters in here. Yeah, I'll put one over here in case you want to use it. So if you want to highlight a real number line to indicate this set, you would put an open parenthesis at 2, a parenthesis that says we're not including 2, and then you would shade with a highlighter everything to the right and just put an arrow on the end. And that indicates all numbers greater than 2, all real numbers greater than 2. And finally, we have interval notation. And since we're not using 2, we use a parenthesis to indicate 2 is not included in the set, just like it is here on the number line. You have that parenthesis. And we're going to the right to positive infinity. We put the positive infinity sign and we close it with a parenthesis because we cannot include infinity. It's not a single number. It can't be included. It's a concept. Okay. So anytime you use infinity, whether it's positive infinity or negative infinity, you always have a parenthesis. If you were including, let's suppose we were looking at this set, all x such that x is greater than or equal to 0. If we were looking at that set, this is not positive real numbers. We have to use this term, non-negative, because it has 0 in it. This is non-negative real numbers. That's a mouthful. But if we were actually putting this on the number line, it would look like this. 0, and I would have a bracket like this. I call it the staple, because if you think of a staple, it's shaped like a bracket, right? And it includes it, right? You include whatever you use the staple with, and then you would shade all the way to the right. So that would be the set of all non-negative real numbers. So you can start your activities by doing interval notation and set builder notation right here. I'll check it off for you when you're done, and then you can just turn the page and continue with sets, okay? So when you get these 2 done, just let me know and I'll give you a little check or talk to you if you have any problems.